Okay, so convex lenses, they're converging lenses, much like a concave mirror reflects light so that it all collects at a focal point, so does a convex lens. We're thinking like a magnifying glass, the kind of thing you'd use to refract light so that it focuses into a point and you can set fire to a piece of paper. This little diagram I've done you here, that's a convex lens sitting there. We'll just draw a small symbolic convex lens, and I've drawn on two rays of light coming in parallel with the principal axis. We've got two focal points on a convex lens. There's this focal point here and also this focal point here. The important thing to remember is that parallel light refracts so that it passes through the focal point on the far side of the lens. And so incident light, light from the sun that comes in parallel to the principal axis, bends as it passes through the lens, and it all meets up at that focal point there. What we're going to do is have a go at drawing ray diagrams and then doing calculations for these convex lenses. We're going to use the same three rules for convex lenses that work for concave lenses, concave mirrors, convex mirrors. It's nice that it's always the same three rules. First rule, in parallel, out through focus. And remembering that our parallel light is going to refract through the far focal point. We're going to do two different examples here. One where the object is outside of the focal point, and a second one where the object is in between the lens and the focal point, because we get two quite different results with a convex lens. Here we go. On the first one, in parallel, out through focus. Making sure that we always put an arrow onto each of our rays. Second rule is just the reverse. In through focus, out parallel, and we need to make sure that we use that second focal point that we haven't already used. We can already see that we've found a point where these two rays intersect. Our third and final ray is to confirm that we haven't stuffed up. In and out, straight through centre. You can see that to draw that ray, I lined up the top of the object with the centre of the lens. And the centre of the lens really is at the centre of the lens. Luckily, all three of those rays passed through that same point, and so we can be confident that that's where the image is. Let's draw on the image. I had a quick measure up of the image, and I found that it was 3 centimetres tall, using my scale of 2 inches is 1 centimetre to make it big enough that you can see it. We need to use 3 words to describe the image. It's upside down, and so we say it's inverted. The height of the image is 3 centimetres. The height of the object was only 2 centimetres, and so the magnification is enlarged. And it's formed with real rays. If we put a piece of paper here, we really would form an image of our object on that piece of paper, and so it is a real image. Let's now turn our attention to this second example down the bottom here, where that object is instead between the lens and the focal point. What's going to change? In parallel, out through focus. In through focus, out parallel, remembering to make sure that we use the second focal point. Immediately we can see we're going to get a different result. And just looking at it, we can see that the in parallel out through focus ray and the in through focus, out parallel ray are moving such that they are never going to meet on the real side of the lens. However, if we put our eye here, our eye doesn't see that those rays bend as they pass through the lens. It just thinks they travel in straight lines. So let's extend those rays back as though they travelled in straight lines and weren't bent by the lens, and see where they end up. When we extend the rays back into the forbidden region, we use dotty rays because that's not really what the light is doing. It's just what our eye perceives the light is doing. Aha! Look, we've found a point here where two rays intersect. Let's draw a third confirming ray in and out straight through centre. And happily, all three rays meet at the same point. Let's draw on the image. So the larger of those two arrows is the image. The image is three words. It's going to be enlarged because it's taller than the object was. It's erect or upright because it's the same orientation as the object was. And it's virtual because it's formed where those rays appear to have originated from, but if we were to put a piece of paper here, we would not form an image on that piece of paper. Let's take a couple of measurements off our diagram and then have a go and see if we can mathematically get to the same point. On the first one, I measured the distance of image using my 2 inches to 1 centimetre scale factor to be about 7.5 centimetres, and on the bottom one to be about 1.5 centimetres. I'm going to pop those up the top, and we're going to see if we can repeat that by calculation. The equation we always use for calculations is the 1 over f is 1 over di plus 1 over do, and in each case we're going to be trying to calculate di, and so we're going to rearrange this equation to be 1 over di equals. Let's start with the first example where we had a focal length of 3 centimetres and an object distance of 5 centimetres. The focal length on a convex lens is positive, it's a real focal point. There we go. So we've gone a third minus a fifth. A nice common denominator is 15ths, so 5 15ths minus 3 15ths is 2 15ths. And we end up with fraction equals fraction, so we can flip both sides and make it 15 over 2. And half of 15 is 7.5, which means we're really happy we've repeated the same di as we got using our diagram. Let's try again for the second lens. Same equation. So here we go. This time, 1 over f was 1 over 3. 1 over do was 1 over 1. Common denominator of 3, so 1/3 minus 3/3. Takes us to negative 2/3. Fraction equals fraction, so we can flip both sides, and we end up with di as negative 3 upon 2, or 1.5 centimetres. The negative sign tells us that the image is virtual.